that's long and wide. Santa's got a beard that's long and white. Who comes round on special night? Santa comes round on special night. Special night, beard that's white. Must be
Milster.
It's like he pulled up the paper and I started pulling up a picture and then he disappeared like an engine.
This is the final lab with the Mach-Zehnder Interferometer.
The Mach-Zehnder Interferometer was first proposed by Ludwig Zehnder in 1891. His proposal was refined by Ludwig Mach, son of Ernst Mach, namesake of the Mach number, in 1892. Like most interferometers, it uses optical path difference to measure transparent objects as well as modulate output light. The setup for a Mach-Zehnder interferometer requires a collimated light source, 2 flat mirrors, and 2 beam splitters. The laser is split by 1 beam splitter and is sent down 2 paths, each to a flat mirror. Both beams are redirected back into a second beam splitter, and 2 outputs consisting of light from both beams is observed. For output 1, path 1 and path 2 are out of phase by pi, so they destructively interfere and no output is observed. For output 2, both paths experience the same number of reflections and path length, so the beams constructively interfere.
Before we discuss how we build this interferometer, it is important to point out that it is very difficult to achieve perfect constructive and destructive interference like this. Placing each component so that they are equally spaced in a square is nearly impossible in the undergraduate lab. Even real optical communication systems don't have perfect modulation like the theory.
When constructing our own Mach-Zehnder interferometer, the name of the game is alignment. We send a laser through a rough construction of the interferometer. Then, adjusting the beam splitters and mirrors, we align the 2 beams together. Then we make the path difference as small as possible. Then we can make finer adjustments with the PZT mount. In order to modulate between the 2 outputs, we need to change the OPL by quarter the wavelength. And given we are using a Heaney, we need to change it by about 150 nanometers.
After some time, we were able to find fringes, meaning that the beams were almost perfectly co-aligned. Once we have perfect alignment, you could see the outputs flicker as small environment changes affected phase offsets of the 2 beams. As seen in our graph, this is not on-off modulation, given that this is pretty much impossible to get given our setup. Based on this plot, you can see that with 4 volts of movement of the PZT, we get a full period of change of one of the outputs. So ultimately, 2 volts of applied voltage to the PZT is equivalent to 150 nanometers of mirror movement. Being able to control the path length with tens of microns accuracy is incredibly difficult. Also, the alignment is so precise that our graph may be shifted due to environmental factors shifting the system in between measurements.
This type of interferometer was and still is used for external modulation of optical communication systems. They minimize the effect of dispersion, which is crucial for such systems. Instead of changing the physical distance between optical elements, Mach-Zehnder interferometers in optical communication control the modulation by utilizing an electro-optical crystal. By changing the voltage applied to the crystal, the refractive index of the crystal changes, which in turn slows down the light in the crystal and introduces a phase shift into one of the arms. When recombining the paths, the phase modulation gets converted to intensity modulation. Essentially, by feeding the crystal modulated voltage pulses, pulses of light are a result.
This interferometer is also commonly used to observe aerodynamics. By placing the object to be observed in one of the arms and allowing air to flow over the object, the output of the Mach-Zehnder is an image of the airflow causing changes in refractive index, and therefore optical path length in one of the arms.
Thanks for watching and happy holidays!